Yes. I'm at work. Thank you. Do, do, do. Do, 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 do. Do, 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 do. Hello, hello.
I'm sorry, that means I'm going to do your copy.
I'm an expert in thermonuclear acid.
All right, good job, guys. All right, just get over here. All right, move it straight. Inside there, about 800 stone.
Okay, can those of you at home hear me okay?
Yes, sir.
Yep.
Okay. Hold on, just getting set up here. Hi. Y'all doing all right? We got a filled to capacity here today. All right, it's 101, so we'll get started. Y'all can see my screen at home?
Yes, sir.
Yes.
Okay, all right, we're gonna get started here. So we left off, where did we leave off? Quadratics, right? We were talking about quadratics last time, and that there are two forms of quadratics. The standard form and the vertex form, they both had pros and cons. I did the homework, the video for the homework, it was kind of cheesy. I skipped over some of the problems. I was hoping that you all kind of got the idea. Were there any questions? Do you all want me to go over anything in terms of graphing a quadratic function? Is there anything that you want me to cover? We're all happy? Yeah.
Use the quadratic formula or factor, right?
Well, the question is, you can either use a quadratic or factor, yes or no. Some things don't factor. So the quadratic formula is like kind of like the one that'll work all the time. Okay, so if you can't factor, go to quadratic. Now, sometimes your quadratic formula will give you a negative under the root, which means that you have no solutions, which means that you have no X-intercepts, right? That's right. Okay, so we're going to move on to the next section. I've already completed the homework videos, or the homework video solution thing for this section we're going to do. The drawback to it is I haven't posted it yet. I didn't have time, so I'll post that later today. So we are going to cover a very important topic related to what we've already been doing, and that is called quadratic inequalities. Now, this topic, quadratic inequalities, it actually pops up all over the place in different math classes that you'll take from here on out. You'll see it again in pre-cal, you'll see it again in Cal 1, Cal 2. It's just in different various places, we have to be able to solve inequalities that are quadratic. So I want to start out first by just talking about inequalities in general, what an inequality is. If we have something like, let's say 4x minus 8 equals 2, this is a linear equation, right? And this is just making sure we understand some language here. It's an equation because it has an equal sign. It's linear because the highest power we see on x is 1, right? That's a linear equation. And to solve that, all we do is move the 8 to the other side, add 8 to both sides, divide by 4, and we get a single solution, right? X is 2 is the only value of x that'll make that equation true. Now, when we compare that to a linear inequality would look like this: 4x minus 8. And I can do, there's there's actually 4 different types of inequalities I could write. I could say less than 0. I could also do 4x minus 8 greater than 0. I could say 4x minus 8 less than or equal to 0, or I could do 4x minus 8 greater than or equal to 0. So the 4 types of inequalities that we have are those 4. Now, I know you have some background with these, so I'm sure you understand kind of what they mean, right? If like the one on the left there, 4x minus 8 less than 0 means that you're trying to figure out what x you can plug in that would make sure that whatever answer you get out is smaller than 0. But it can't be 0, it has to be smaller. And then the next one would mean that whatever x plug in, it would have to be greater than 0. And then the only difference on the 2 on the end is that those 2 you can actually be 0 also. So with the linear equation on top, we have one answer. With linear inequalities, we have an infinite number of answers. So let's look at how we would solve one of these. Let me do this one. The way we solve, I should have put here linear inequalities. Does anyone know how to solve these? Yeah, it's same as the equation. Inequalities. Okay, so these linear equalities, it's basically the same thing as an equation, right? You're going to take this 4x minus 8. You're going to say less than 0. You can add 8 to both sides. Oops. So you get your 4x less than 8, and then you could divide by 4. And so you get a solution that says x must be less than 2. Now, on a number line, that's every value of x that you can come up with that's smaller than 2. So if I visually, I can't draw a straight line today. Here's 2. Our answers are everything to the left of 2, right? Smaller than 2. And what about 2 itself? Can 2 be there? No.
No.
Because 2 would make it equal 0, right? And we want it to be strictly less than 0. So it'd be, I do something like this, open circle, and then everything this way forever. As an interval answer, I would write negative infinity to 2 with a parenthesis, and that would be the interval answer. So the good news is that for linear inequalities, you pretty much do the same thing you do for linear equations, with one exception. Do you all know what the exception is? Yeah, there's one tricky spot. If you have an inequality, a linear inequality, and if you ever multiply or divide both sides of the equation by a negative number, then you must flip the inequality over. So I'm going to show you all how that works. I'm actually going to take the same problem and I'm going to work it a slightly different way. 4x minus 8 less than 0. Okay. So what I initially did in the previous version of this, I added 8 to both sides, right? Just for the sake of demonstration, I'm going to instead subtract 4x from both sides. Okay, that's a legal move. And I'm subtracting right now by a negative. That you don't flip now. You only flip if you multiply or divide. So they go away. On the left, I get negative 8 less than negative 4x. Now, I want that x by itself, so I'm going to divide both sides by negative 4. Here's where we start to have the issue. Okay, on the on the right side, it goes away. I get x. On the other side, what would I get? Just
Positive
2. Right? Now look at this. If I do not flip, okay, don't write this down, but if I don't flip it, what is it saying my answer is? Everything bigger than, right? All values bigger than 2, but wait a minute, isn't it supposed to be all the values less than 2? So the reason why this would be wrong is because I failed to flip this. I have to flip it. Flip. Oh my gosh, come on. Flip it, okay? Because I divided both sides by a negative number. So anytime you multiply or divide both sides of an equation by a negative, you have to flip. And now that answer is the same as the answer above, right? That's saying 2 must be bigger than X or X is smaller than 2, same solutions. Is that okay? That's not what today is about, but I just want to make sure we understand this before we move on to the quadratic inequalities. We good at home? Okay, I'm not going to do these 3. Okay, these 3 we'd have different answers if we did these 3, but I'm going to move right on to the quadratic inequalities now. All right, just a little bigger. Okay, so quadratic inequalities. So I'm going to do this. I'm going to do this in 2 different ways. I'm going to just compare an equation versus an inequality, just so we can, again, side by side, see the difference. So the first one's going to be a quadratic equation. That's a quadratic equation. We studied those last class, right? We know how to solve those from last class. And then over here, I'm going to put a quadratic inequality. So here's the bad news. Let me put the inequality. X squared minus 4x minus 5. I'm going to put less than or equal to 0, okay? So the big difference between those two, the only thing that makes them different are those symbols between them, right? One of them is what X values make that equal 0. The other one's saying, hey, what X values make that less than or equal to 0. So the bad news is that you cannot solve it the same way you do the equation. Like with the linear, we had this basically it's the same thing. You just have to be careful, flip if you divide or multiply by negative. When you have an inequality on a quadratic, it's a completely different process. And so as you move on in other math classes, you don't want to make the mistake of trying to treat it like an equation. So let me do the left side first. If it was an equation, we would just factor it. You could use a quadratic formula, okay? If you weren't comfortable with the factoring, you could use quadratic. Set each of these equal to 0, which I'm going to trust you could get these 2 answers, 5 and -1, all right? These would be our 2 solutions to that equation, right? 2 answers. And we know from our discussion of quadratics that you're only ever going to get 2 answers or 1 answer or no answers, right? For quadratic equations, but it's impossible to get 3. Okay, now with the quadratic inequality, it's a little different because we're basically saying what values of X will make that thing less than or equal to 0. So here's the procedure, okay? The procedure for this is always to do this. First, you will set it equal to 0. So that's the first step, is that you ignore the inequality completely and you just treat it like an equation. And then you find the solutions, which I already did on the left-hand side. So we already know the 2 solutions to this are 5 and -1. Now, I'm not saying that these are my answers. I'm saying this is the first step. I just set it equal to 0 and get the answers. The next thing is to plot those answers on a number line. So I'm going to draw a number line. And I'm going to plot -1 and 5 here. And then what I'm going to think to myself is, well, that at -1 and 5 is where this thing is equal to 0, right? It's where it's equal to 0. So I know that that's where this thing hits 0. And I want you to think of it as like a parabola, right? We were looking last week on how do you graph parabolas. So look at what's in that blue right there, okay? If I were asking you to graph that, that's a parabola. It opens which way? Up, right? And what you're asking is, when does that parabola when is it ever less than or equal to 0? So doesn't that mean you're asking, when does it go below the x-axis? Okay, but we already know where it hits the x-axis here, don't we? So we could imagine, we don't need this, but we could imagine that we have a parabola. I don't know the exact shape of the parabola. I don't know exactly where the vertex is. I could figure it out, but I'm just trying to imagine that there is a parabola that opens up that goes through those 2 points, right? And I want to know where it's less than or equal to 0. which means I want to know where this thing is below the x-axis, which corresponds to this piece of the graph. There we go. This piece of the graph right there. And that happens when we are in this region between -1 and 5, right? Anywhere in here, if you plug in a value from that little interval, it's going to spit out a negative number below it. So my answer should be everything between -1 and 5, including -1 and 5, because again, we wanted to know where it was less than or equal to 0. So we do want to include these two endpoints. So I could make those solid dots as included in part of my answer. And so the solution set in interval notation should be a bracket, -1 to 5 with a bracket.
Will it always be between the two numbers that we get when we equal it to 0?
No, that's a good question. Will it always be between? So what if the original inequality would have said x squared? Well, let's just write it. What if it would have been 4x squared minus 5x? Wait, hold on. Minus 4x. So I don't know what I'm writing. What if the original problem was x squared minus 4x minus 5, let's say greater than 0, right? So how would this change? This is a different problem. Well, we'd still do the first step, which would be to set it equal to 0. So if we do that, nothing changes. We still get two solutions, -1 and 5. That makes sense? Number line now. -1 and 5. And then I imagine my parabola. It's the same parabola, right? It opens up. So it's the parabola that I'm kind of envisioning. Comes down here, goes like this, and goes up, right? But this time, I want to know where this parabola is greater than 0, right? Where is it bigger than 0? So that means where is the graph above the x-axis? And that's happening here and here, right? Which corresponds to x values that are to the right of 5 and to the left of -1. Now, in terms of -1 and 5, do I want to include them this time? No, right? Because if I plug in 1 or -5, I'm going to get 0. And this inequality says strictly greater than 0. So I want to leave these as open. And so do y'all see that that's not the stuff in between? You see that it's actually the interval notation of this answer would be -infinity to -1. Don't include -1, so parenthesis. Union, now 5 out to infinity, done. Does that answer your question? I didn't see who asked.
Yes, it did.
Okay. Yeah, I wish it was always just find the x-intercepts and it's what's in between them, but it's just not that way. It depends on the inequality itself. Now, just to show you, okay, I just want to show you, and I hate showing people the wrong way to do it, so maybe don't write this down. This is what I see from students later on in some other class. They go to do this problem, like the first one I gave you here, this one right here, and they do this. They factor. And then they do what you normally do with an equation. They say, oh, that means x minus 5 has to be less than or equal to 0. And then x plus 1 has to be less than or equal to 0. See how it's almost like the same thing as solving the equation, just setting each one equal to 0. They set each one less than or equal to 0. And let's see what happens here. If we add 5 to both sides, we get x must be less than or equal to 5. Here we get x must be less than or equal to -1 by subtracting 1 on both sides. And now if I think about what this is saying, I have -1 here and I have 5 here. This first answer says anything to the left of 5, including 5. So anything this way forever. And the second one is saying, anything less than or equal to -1. So anything to the left of -1, which is already included in what you got before, right? And so that's everything basically to the left of 5. So you'd say, left of 5, negative infinity to 5 bracket, right? And this is completely wrong. Okay, because I can probably convince you by I'll give you an example. Like the number 0 is in here, right? The number 0 is in here. But if you try plugging 0 into this original thing, let's see what happens. 0 here kills all this off, and you get, oh wait, that does work. Sorry, negative 5 is less than or equal to 0. What wouldn't work? Negative 2 wouldn't work, right? Try negative 2 in here. It won't work. Negative 2 squared is 4. Negative 4 times negative 2, that's 8. So you're going to wind up getting 4 plus 8, that's 12. Take away 5, that's not a negative number. So something is wrong. And what's wrong is basically I'm not doing it correctly, all right? That's not the way we solve quadratic inequalities. So that's pretty much the method. Understood? All right, so really there's not a whole lot more other than to give you some problems to try yourself. So why don't we work on a few here? And then once we do a few of these and we feel comfortable, we're going to move on to the next section. All right. So how about this? I want you to solve. Let's go 2x squared minus 5x plus 2 greater than 0. Solve 3x squared plus 2x plus 8 less than 0. That'll be interesting to see what happens there. Then solve 5x squared less than or equal to 4x plus 8. So I'm going to let you all work on these right now, okay? The first one I think will be straightforward as long as you can solve the equation. Second one's going to be a little tricky, I think. The third one's not that it's hard, it's just you got to move things around a little bit first. So I'll give you some time to work on these. If you have a question, just let me know. Any issues? All right. Any issues at home? I think what I'll do is I'll work these out while you work them out. I'm just going to kind of work them also. So I got the first one up there worked out. I'm just working these out for y'all at home. I think I was on mute and didn't tell you. I'm just working them out, letting you work. If you have any questions, let me know. Have y'all finished the first one? First one. Bobby, are you still working on it? Did you get this? Use quadratic formula? Yeah. It's all right. And then you work out 3, 2, 5 plus 3. Oh yeah, 8 over 8 over 4. Okay, good. Let's talk about the second one. The second one is kind of interesting. No questions on the first one? The second one's kind of interesting because it does not factor. Well, I don't think it's, does it factor? Yeah, I don't think it factors. So you have to use the quadratic formula, right? You have to use quadratic formula. So when you go try to use quadratic formula, you'll do negative b plus or minus square root, b squared is 4, minus 4 times a times c all over 2 times a, 2 times 3. And you're going to run into a problem here because underneath the root, this 4 times 3 times 8, when you take that away from 4, it's going to be a negative number. And so you have the square root of a negative, which we can't do, right? Square root of a negative. So that means that there are no solutions to this, no real number solutions. Right? Understand that? Bobby, you good? So if there are no solutions, that means this parabola does not hit the x-axis. So if I were to go and try and draw a number line and say, oh, okay, you know, where does it hit? It doesn't hit. But I know it opens up, right? We know this opens up. We know it opens up because the 3 out front, right? So because it opens up, that means that it has to be above the x-axis. It has to do something like this. Because if it were opening up and it were below, right, a little bit below, then I would have 2 x-intercepts. Does that make sense? It's kind of like just thinking through that it has to open up, can't hit the x-axis, so it's got to be above. Which means we're asking ourselves, when is this parabola, right? The original question is, when is this parabola smaller than 0? Never, right? This parabola is never below the x-axis ever. So that means our answer is what? How do we say there's no x's that make this true? So we actually have a symbol for it, okay? You know how if we have an answer, we put our answer in interval notation like this? There is a symbol that we use to represent that there is no answer. And it's called the empty set. It looks like this. It's like a 0 with this little diagonal line through it. It's called the empty set. The way I like to look at it is this. When you talk about an interval, like up here, when you're talking about an interval, I like to look at it as like a basket full of answers. This first interval says, oh, you got this basket. It's got all these numbers between -infinity and 1/2 of them. And then you have a union, so you got this second basket that has all these numbers between 2 and infinity, right? This problem that we just did, we have no answers, right? So I have a basket that has nothing in it. It's this empty set. You can't say 0 though, because 0 is actually a number, right? So you can't say the answer is 0, so it's not that. So we have just a different symbol for it. Now, if anybody here has a military background, that is the way you write the number 0 in military. So you don't confuse it with an O, right? From the letter O. So it has 2 meanings. In the military, it is the number 0, but in mathematics, it is the empty set, all right? So that's how we would write it, all right? And I believe in the homework, it just says, in multiple choice, it just says, either put in the interval answer or it says no solution. It doesn't talk about empty set. I'm just showing that to you for your own sort of benefit, I guess. All right, this last one, the big difference here is that you have this quadratic inequality, but not everything is on one side. So the first thing you want to do is move everything to one side. And I would recommend leaving the 5x squared where it is, bringing the 4x over as a -4x, and bringing the 8 over as a -8, and then making it less than or equal to 0. And then you go through and do the same process. So you set it equal to 0 first. And then you use your quadratic formula. ... Did anyone do that? Did anyone get 2 answers here yet? What'd you get?
0.92.
0.92. And what? 1.72. Okay. That sounds reasonable. I'll check it in a minute. I'll graph it. Oh, negative 0.092. Okay. Negative 0.092. Wait, 0.092 or 0.92? 0.92. Okay. So those are your 2 x-intercepts. Put those on a number line. Negative 0.92 and 1.72. You know, when I was a student, I used to get kind of confused because some of my teachers would write negative 0.92 and others would write negative 0.92 without the 0. Those are both correct. You can write it either way. The advantage of writing it with the 0 first is just in case you're not paying attention and you don't see the dot there, that's a double dot. But sometimes someone will put a decimal there and it will be so light that you can't see it. So you might accidentally think that that says negative 92. But if you put a 0 in front of the decimal, if you didn't think that like if you didn't see the decimal, you'd be like, what the heck is what is 0.92? That just seems weird. Like, so the 0's there to kind of stress, hey, look, that you should be looking out for a decimal point. Otherwise, you can write it either way, all right? All right, so here we are. This again is a parabola that opens up. And we want to know when it was what, less than or equal, right? Less than or equal to 0. So we're looking at this region here. And we do want to include those two endpoints. So it'll be everything between those two numbers. So it should be bracket negative 0.92, comma 1.72, bracket done. We good? Questions at home? All right. I don't recall. Did I give y'all? I don't think I gave it to you. Okay. I didn't give you all the equation for objects that fall on Earth, right? I don't believe I did. Okay, good. So I'll give that to you now. All right, so this will be better for the people who are here in class. I actually don't even have a book to do this with. Oh, here I have something. I'm gonna have like a sacrificial little piece of paper. And piece of paper. I'll try and move my camera so y'all can see me at home. Yeah, there we go. Thank you. All right, this might be a little bit loud for those of you at home. What I have here is a little notebook and I have a little sheet of paper. So what I'm gonna do is I'm gonna drop both of these right now, okay? And I want you to predict which one's gonna hit the ground first, right? This little notebook or the piece of paper. Everyone got their pick? Now you at home, you're not gonna be able to see this, I don't think, but the people in class will let you know what happened. So you ready? 1, 2, 3. Okay, so the notebook hit the ground first, right? And then the paper kind of floated its way down. So why did the notebook hit the ground first?
It's heavier.
Does it have anything to do with which one is heavier?
Yes.
What's that, Tom? Notebook's heavier, so that's why it lands first. I heard that at home also, okay? So it turns out that it has nothing to do with the weight, okay? This could be a bowling ball and a feather, all right? If I drop them, they should drop and hit the ground together, regardless of their weight. The reason it doesn't happen that way is because of air. The air resists, has a bigger impact on the piece of paper than it does on this. And to prove it to you, here's what I'm gonna do. If I put the piece of paper on top of the notebook, and see I'm not taping it there, it's just right there, right? So if your theory is that it's because of the weight, then what should happen is when I let go, the heavier one should drop away from the paper because it's heavier and falls faster, and the paper should just float behind it, right? But watch what happens. They go together, okay? So the reason they went together is because now the notebook is moving the air out of the way, right? So the air is no longer this is no longer impacted by the air. So it's free to fall at the same rate that this one is. So this was, a pretty big thing to figure out. Humans figured this out that, hey, look, if you take air out, everything drops the same. In fact, one of the experiments that we did when we actually went to the moon, if you believe we went to the moon, and so many people think we that we didn't go to the moon. One of the first things that we did, and there's video of it, of a guy, an astronaut out there, he's got a hammer and a feather, and he drops them both, and they both hit the ground at the same time. It's because the moon does not have an atmosphere. There's no air up it. Now, we already knew, we had already proven it. Okay, like humans had already proven it on Earth using vacuums that was true, but it was almost like a mic drop, kind of. Like we went up to them and we're like, yeah, there you go. You know, because a lot of times science has been in complete conflict with what society believes, like the culture. So there was a point in time where we thought that the Earth was the center of the universe and everything went around us. And if you said otherwise, you know, you were taken out to the gallows, you know, like there's just a lot of times where scientists had trouble that were actually persecuted, put to death because they spoke out against something. And yeah, so anyways, we figured it out a long time ago that on Earth, all objects should drop at the same rate if you take air out, okay, if you take air out. And that means if I'm standing on a 40-foot bridge and I drop a rock and I drop a feather, I should be able to predict at every moment in time where they will be if air is not there, right? Now, I understand, like, you're like, well, air is there, right? So we have ways of accounting for that, but it becomes more complicated. And so our formulas become more complicated. So we always like to crawl before we learn how to walk, before we learn how to run, right? So if you want to look at the most basic formula we have for objects that fall on Earth, if you take air out, it's a quadratic function. Okay, if you remove the air from the equation, it's quadratic. And here's what it looks like. And for most practical purposes, this equation is okay. Like if you're dropping a rock off a bridge, this formula is good enough because air doesn't have as much of an impact on a rock as it does if you were dropping a piece of paper. So we use this formula quite a bit. If you want to be precise, it's a different formula. So here's what it is. Let me write it down first. It's D. I'm going to adjust it a little bit. I'm going to put H of T equals -16 T squared plus V with a little subscripted 0 underneath that, T plus H with a little subscript 0. So this is the formula that will give you a lot of information about any object dropped on Earth. All right, so here I need to tell you what all these letters mean. Okay, so first of all, let's start with the T. The T is like the X has been in previous quadratics. The T is just time. And it's measured in seconds. In this formula, it's measured in seconds. All right, H of T, which is the left side of the equation, is the height of the object at exactly T seconds. So T is a variable. You plug in a value of T, like let's say you plug in 5 seconds. This formula should spit out exactly how high the object is off the ground after 5 seconds. Now there's other things in here. H with that little subscript 0. We say that H naught. You all heard that before? H naught. It's a physics terminology. Naught, I think it's N-A-U-G-H-T. H naught. Not meaning zeros. So this is the initial height. And this is measured in feet. Also, I should say that above that, the height of the object after a certain number of seconds is also measured in feet. Okay, so H naught is how far up, let's say, the rock is before you drop it. So if you hold a rock 6 feet off the ground, H naught is 6. If you take a rock up to the top of a building, right, it's 200 feet high, then the H naught is 200. Now V naught, this is an interesting number here. This is the initial I misspelled that initial, didn't I? Sorry about that. Initial velocity. And this is measured in feet per second. So I need to explain this because this can be a little bit complicated. Let's see if I can use one. I know you at home, this can be hard to see, but I have two markers in my hand. If I just drop these and let these go, they're going to fall and hit the ground at the same time, right? So if I just let them go, then my initial height, my h sub 0 is how far off the ground they were when I let them go. My initial velocity, if I just let them go, is 0. Meaning all I'm doing is letting them go. I'm not giving them any acceleration. I'm not like throwing this one down or throwing this one up. So let's see, if I take this one and I throw it up in the air, and I take this one and let it go, then they're not going to hit the ground at the same spot, same time, right? It's different, right? Because I gave that one over here a little bit of an initial speed up. Same thing, if I take them and I take this one, instead of throwing it up, I throw it down, it's going to hit the ground before this one if I just drop it. So I mean, it's obvious stuff, right? But that initial speed I give it has to be accounted for in the formula, and that's what the V naught is. So if you throw it up, then that V naught is a positive number. Okay, so I need to put that here. Positive if up, and negative if down. There's a classic example of you have like a helicopter that's hovering and it has a bomb, and the helicopter starts rising up, right? Rising up, rising up, rising up. And as it's rising up, it decides to let go of the bomb. Okay, so the helicopter was coming up, it releases the bomb goes and drops, right? When it released the bomb, did the bomb go up or straight down? It actually had to come up a little bit before it started going down. Because as the helicopter is moving up, it's got a velocity going upward. And so when it cuts the bomb loose, right? The bomb still has that inertia, it's still moving. It goes up a little, I'm going to exaggerate, the bomb goes up with it and then starts to come back down. So you have to account for that initial velocity. Now, if you just drop it, V naught 0, and we're happy, we move on, okay? That's our formula. That is a formula for all objects on Earth, no air. So I'm going to put up here height of falling objects on Earth, no air.
Where does the negative 16 come from?
I'm glad you asked. I was just about to talk about that. The negative 16 has to do with the acceleration of gravity. So if you may have heard from a physics class or somewhere else that the acceleration of gravity is negative 9.8 meters per second per second. Have you ever heard that? So if you convert 9.8 meters per second over to feet per second, you get 16, negative 16, I should say. And so really at the end of the day, this is the only number that is dictated by the fact that you're on Earth. If you go to the moon, it's still a quadratic. It just has a different number in front. If you go to another planet that has different gravitational acceleration, that number changes, but everything else is the same. And so a quadratic will always model how something falls on any planet with mass, so long as you know the acceleration of gravity. Good question. Okay, so this is it. Now, what can we do with this? I realize we're not talking about air, and I know that that should bother you a little bit, but like I said, you crawl before you walk before you run. So that's why when you look at a physics book, right, and you see all these very complicated formulas, it's because we have to take into account so many different things, right? If I drop this, rag, right, then there's a lot of things that are at play here. The air, not only the air, the texture of the rag, what kind of friction that causes with the air. Do I just let the rag go, or did I rotate it? Did I spin it? Is it spinning? Is it just free? You know, all the, if you want to account for that, your formulas are going to have to be much more complicated. And so that's why physics becomes hard, right? It's so many variables. Think about the weather, right? We try and predict the weather. How many different factors do we have to, how complicated are those formulas, right? That's why when you watch the news these days, if you ever do, and they're trying to tell you what the weather is going to be like, they're like, okay, we have like 5 computer models that are saying it's going to do this. It's because there's all these different algorithms that you could use. And what they do is try all these different ones. And they kind of say, it looks like maybe it's like the average of all of these or something. And it's still an imperfect science. So, okay. But as far as falling objects, if you take air out, we're in business. Okay, we can predict what's going to happen. So let's see, how can we use this? How can we use this and tie this into quadratic inequalities, right? So I'm going to give you a problem now, and we're going to work through this. Okay, let's just do a rock. I know it's boring, but we're just going to do it. A rock is thrown upward with a velocity of 25 feet per second from a 48-foot bridge.
I'm sorry, Professor. Were you wanting to do 20 or 25 for the feet?
Did I say 25 and write 20?
Yes.
Oh, let's go with 20. I'll go with what I wrote. Sorry about that. A rock is thrown upward with a velocity of 20 feet per second, or with a velocity of, 20 feet per second from a 48-foot bridge. All right. Here are the questions. First, part A, find a quadratic function which gives the height of the rock as a function of time. So the first thing we want to do is convert this word problem into a function. The second thing we're going to do is find the maximum height. I want to know how high that rock's going to go. The next thing I want to know is when does it reach the maximum height? The next thing I want to know is when does it hit the ground? And the last thing I want to know is when is it higher than 15 feet. Lots of questions. All right, ready to start talking about this? First thing is the function, right? So I gave you a generic function. This generic function, the only thing it needs to work is you have to tell it what the starting height is and what the starting velocity is. I've provided both of those, right? the height was 20 feet. No, the height was 48 feet and the velocity was 20 feet per second. And I said it was thrown upward, right? So we're going to use positive 20. So this formula becomes h of t equals negative 16 t squared plus 20t plus 48. That is the quadratic function that will give you the height of this rock after some amount of time if we neglect air, right? Now, what is part B asking us for? The vertex. Yes and no. It is the vertex, but see, the vertex is a point, right? So we all have to understand that what we have here, this quadratic, is a parabola that opens down. Do we all see that? This is a parabola that opens down because it has a negative 16 in front, right? And so it should have a highest point, shouldn't it?
Wouldn't we be looking for it at when time equals 0 or like 0.0001? Technically, as soon as to the release as we can.
Well,
assuming
remember,
we're throwing the rocks, so
yeah, but we're throwing it up, right? So it's
Yeah.
actually going to go up higher and then start coming back down, right? So if this parabola models the height, then to say what is its maximum height, here's what I can do. Maybe I can help us with this way. If we were to imagine that we have time on this axis, right? And we have the height on this axis. From the given information, at time is 0, how high was the rock? So when I let it go out of my hand, how high was the rock? 48 feet, right? By the way, I'm kind of neglecting the fact that I might be standing, like 48 feet is where the rock left my hand, okay? So the rock is thrown up, right? So as time goes on, the rock goes up, comes back down, and hits the ground, right? Like this. That's kind of the picture of what we have. And so to say, what is its maximum height? This point, HK, isn't H like the X coordinate? Isn't that a measurement of time? And isn't the K the Y coordinate? And wouldn't that be the measurement of the height? Understand? Tyler, you understand?
Do you mind if I'm a little difficult for a second?
No,
for this?
Go ahead.
But we don't actually, unless we were given this graph, if we were just doing it based on the word problem, we don't know how hard they threw it or where they threw it at. So we don't actually know at how long it took for it to actually go. Because as far as I can tell, there's no actual way to determine that based on the problem, unless we were given the amount of time it took to reach the vertex.
Well, we were given the velocity of the rock as it left the person's hand, right?
Mm-hmm.
So the velocity of the rock when it left the person's hand is 20 feet per second. Okay. Yep. We're given the height at which it left the person's hand. That's all you need. That's what I'm saying about this formula. This formula will always tell you exactly where something is. All you have to provide me is how high it was when you started and what the initial speed was. Because as soon as it comes out of your hand, right? As soon as it leaves your hand, the only thing acting on it is gravity, right? This formula accounts for all of that. And it tells you it's going to start to slow it down. The rocks are going to go up, slow down, hit a maximum height, and then start coming back down. So there is enough information because this formula kind of guarantees it. I don't know if that satisfies or if I'm addressing your question properly.
It does to a degree.
Okay. If this were, let's say, like a rocket, it would be a little different because a rocket, when you launch a rocket, it's still, it's got propellant. It's like, there's a force, right? So it's constantly there's two forces. It's the force of the rocket and there's force of gravity. So this is a free falling object where the only thing acting on it is gravity, but you are allowed to give it some initial velocity upward or downward.
May I ask a quick question?
Yeah.
Is velocity equal to like force? Would it be like when I throw it up, the velocity is the force of?
It's not the force. It's not the force. It's a measurement of the speed at which it leaves your hand. Okay, so like if I do a small amount of force, right, then I'm not going to give it much speed going up, right? If I give it a lot of force, then when it leaves my hand, it's going to go with a much bigger velocity. All we're telling you is the speed it left your hand. Now,
Velocity
there are ways in physics. Wait, go ahead.
Velocity is a byproduct of force. Is there another way?
Yeah, so there's a way that you could calculate the force, okay? You could calculate the force. If I told you it was 20 feet per second, you could calculate the force. But then what you would need to know is what was the mass of the object and their, acceleration of gravity. Then you could figure out the force. But once it leaves your hand, the force you put into it doesn't matter anymore. All that matters is the speed it's moving. Its mass no longer matters. Nothing matters except this formula will bring it back to the ground, right? For all objects of all masses, right? That's the beauty of the formula. That's the beauty of the idea that everything will drop at the same rate, is that it's independent of mass. Yeah, because it takes a lot more force to throw a 40-pound rock into the air than it does to take a half-pound rock into the air. But once they're thrown in the air, if they both have the same initial velocity going up, then they're both going to go up and come back down, hit the ground at the same time. It's interesting. Okay, so from this graph, can you see the basic idea that you have a quadratic function and that the highest point that it reaches will be the k of the vertex? So to answer part B, we actually need the k of the vertex. Well, how do we get k? It's the y value, right? But we need to get h before we get k, right? We always got h, then we got k. Well, what is part C asking for? When does it reach its maximum height? So if you look back on this picture, this point represents its maximum height. The h is when it would reach that point, right? And the k is the actual height. So this part C is actually asking for the h from the vertex. Now, what about when it hits the ground? What is this asking us? When is the height 0? In other words, set the
velocity equals 0.
Right? Nope. Right. When is the, wait, say that again.
What you would do is you would look at it when velocity is 0, because if it's on the ground, you've no longer got velocity.
Well, I agree. Once it's hit the ground, the velocity would be 0. I agree with that. But we do not have a formula for velocity. We only have a formula for height, right?
True.
So if you wanted to know when it hit the ground, you would want to know when this height is 0, right? What value of t would make this height 0? So you want to set this quadratic equal to 0. It's like the X-Intercepts, isn't it? It's like the X-Intercepts. On the picture, if you see the parabola here, this point right here is an X-Intercept, right? Kind of like an X-Intercept of the parabola. And we're going to get two answers, aren't we? There's another answer that you're going to get that should represent the parabola on the backside, right? The problem is that answer is going to be negative. And that means that time is negative, and that will throw that answer out, okay? Because it won't make sense to have negative time. So we'll only have one answer for that. And what is the last question asking? That's right. So it's asking, when is this height of this object bigger than 15? This is the quadratic inequality I was talking about. This is asking, when is negative, hold on. It's asking, when is negative 16 t squared plus 20t plus 48, when is that bigger than 15? And that's what we started class with, right? That's a quadratic inequality. So you move everything over to one side and then you go through the steps. Understand? From the picture, if you look at this picture, 15 feet, I don't know, it's somewhere around here, right? Maybe around here. So when you go solve your inequality, you're trying to figure out when is it above this, right? This imaginary line. That should be all in here, shouldn't it? So go solve your quadratic inequality and get your answers. But be extremely careful because remember, time starts at 0. So if you get a negative answer, you don't want that. So I'm telling you all this, I'm setting this all up for you. I want you all to do this problem and turn it in to me next time, all right? So if you come in face to face, you can hand it to me. If you're at home, then you'll just have to submit it through, I'll put a link where you can upload your work, okay? So let's make this like a quiz problem. I think I pretty much set it all up for you. You just have to go execute all these little steps. You're going to probably need the quadratic formula. So while we're talking about, objects falling and stuff, I have something to consider, all right? Let me get my markers again. All right, so imagine that I have, these are 2 bullets, okay? These are bullets. And what I'm going to do is I'm going to hold one bullet with my fingers, and the other bullet I'm going to put into a gun, all right? And I'm not going to aim it over the top. I aim that way, okay? So I have a bullet in my fingers, and I have this bullet's in a gun, and I have them pointed horizontal to the ground. And so what I'm going to do is I'm going to fire this one out of the gun, and I'm going to let this one go with my fingers. And I'm doing it exactly the same time, okay? So I go 3, 2, 1. I let this one go. It starts dropping. This one starts firing out of the gun, and they go. So which one hits the ground first? Same time. So will the bullet from the gun take longer to hit the ground because it's moving to the side, or will they both fall at the same rate? Well, again, it turns out that the horizontal motion of an object has nothing to do with the rate at which it falls. So if I do that, if I fire this bullet and I drop this bullet with my fingers, the time it takes this bullet to hit the ground is the same amount of time it takes this bullet to hit the ground. So if you look at the path of those bullets, okay, if this is the ground, one bullet started here, and I dropped it and it just fell, okay? The other bullet started right next to it, okay? That's a hollow point. And it fell, but it actually moved to the right at the same time. So it was like a parabola, a very, very, very flat looking parabola, but it was parabolic. They will hit the ground at the same exact time, which a lot of people don't realize that's what happens. That's why, these military snipers, they have to learn this so that when they're aiming at something really far away, they have to compensate for the drop of the bullet because it's going to drop no matter what. So they have to aim somewhere else. Well, they just adjust their scope, but they have to be aiming somewhere else so that the bullet will actually hit the target, right? And then they have to compensate for wind and, temperature, all these different things. But so the reason I'm bringing this up is what's really interesting, which I think is really interesting, is that Well, let me do this before I say it. If you have, let's say I fire that bullet and I have a target that's really close. So let's say my target was right here. Then I'm probably going to hit that target right about there, right? But if I move that same target further away, now I'm going to hit that target lower, right? If I move that target even further out, I'm going to hit that target even lower. So if that target was kept at the same height the whole time, then if I move it up or back, I'm going to hit it in different places, right? You agree? Understand? Now, bullets, when they come out of a gun, they have velocities. They have different speeds, you know, depending on the type of bullet. They can come out really slow or they can come out really fast. If I have a bullet that comes out really fast, really, really fast, faster than this bullet, then what will happen is it will still drop, okay? It'll still drop, but it will go and it'll travel a lot further as it's dropping. Okay, it'll still take the same amount of time to drop, but it'll go a lot further. And so the difference, the drop here is not as significant. So you got to know a lot about the bullet you're firing, like how fast it's coming out of your gun, all that stuff. It's complicated. Now, why I wanted to tell you this or show you this is because, have y'all ever heard the phrase like the moon is falling? You ever heard that before? The moon is falling, no? Yes. So if you were standing on Earth, right? And imagine that you fired a bullet, right? So fast that as the bullet went out, it was traveling so fast, it starts dropping, right? But what if it was so fast that as it dropped, the Earth actually started to curve away from the bullet? So the bullet's coming out, it's going, and then it's going so fast that as it starts to drop, the curvature of the Earth starts to drop also, right? If you get it just right, then what will happen is you'll get caught in this perpetual loop where the bullet is falling towards the Earth and the Earth is curving away from the bullet, and it keeps doing that, and it comes all the way back around, and it keeps continuing wanting to fall, and it keeps coming around, and it just gets caught in this loop. And that's what orbit is. That's when you hear about these satellites that are in orbit, that's exactly what's happening. You have the Earth. We have to launch this thing up into the space, right? Up into the sky. We take a rocket, we launch it, and we get it going real fast, and we get it going to this perfect speed. And then once we get there, we cut the engines off and we just let it go. And now it's falling towards the Earth, but the Earth is curving away from it. And it just gets stuck in orbit. All these satellites out there doing that. Now, if you launch it a little bit higher, then it's a different speed that you have to get it to, but then once you get it there, it'll just get stuck. Right? Now, what's another thing you can do is, remember the Earth is turning, right? Like the Earth is rotating. So what we try and do is, you know, it's hard to draw this, but imagine that this Earth here is turning. Let's say it's spinning this way. Okay, going around, that's day and night, right? 24 hours for it to go around. What would be really cool is if you could somehow launch a satellite to a certain height at a certain speed, that when you cut the engines off, it's falling towards the Earth, but the Earth is rotating at the same rate that it's falling. So from Earth, it looks like the satellite is just above the same spot the whole time. And what do they call those? Anyone know what they call those satellites? The ones that are like, that appear to be stationary? Even though they're falling, they're going with the Earth. I think they call those geosynchronous satellites because they basically stay above the same spot the whole time. So we like satellites like that because if you want to spy on someone, right, you can have one satellite just sitting there the whole time over the same spot, falling and taking pictures the whole time. So anyway, interesting stuff. It's all tied into, you know, this parabolic path that becomes a falling path. It's kind of cool. All right, so y'all understand what I want y'all to do with that? Just one problem there? Okay, and then you can do your homework assignment also. Your homework assignment is going to be a lot easier. It's just, you know, solve the quadratic inequality, solve the quadratic inequality. All right, I'm ready to move on to the next topic. unless y'all want any further discussion over quadratics. All right. We're going to talk about polynomial functions now. Poly means what?
More than one.
More than one, many, okay. Polynomial, what's a nomial? Nomial, you could look as a number. So let's look at, let me show you two things. Let's go back and let's take a look at a function like this. F of x equals 3x plus 4. That's a linear function, isn't it? A linear function. And then here's another function over here. I'll call it g of x. Here is something a little more familiar because we just started looking at, or just studied these. That's a quadratic function, right? This first function, the linear one, has two terms in it, right? The quadratic has three terms. Terms are separated by addition and subtraction, yes? So a monomial is basically a number times a variable. And that variable can be raised to different powers. So do you see that 3x is a monomial? It's a number attached to a variable. What is the power on that variable? 1. Okay, 4 is also a monomial. It's a number attached to a variable. Wait a minute, I don't see a variable. You have to imagine that there is an x to the 0 power attached to this. So in fact, it is also a monomial. Here is a monomial, x squared, with a 1 in front of it, right? So a number in front of x to a power. Here we go, we got another one and another one, right? A polynomial is just many nomials. That's it, put together. But there's no restriction on how many. A linear function, right? A linear function is an example of a monomial, a polynomial, where we have the highest power of x we see is 1. A quadratic function is also a polynomial, but we have the highest power of x being 2. So in general, okay, a polynomial is going to look like this, a polynomial function. It's going to be some number in front of x, right? And that x will be raised to some power. So I'm going to write that down. I'm going to have some number a times x to some power n. I don't know what the power is. It could be x squared, could be x to the first power like the line, or it could be x cubed or x to the 4th or 5th or 6th. Then plus another number b, x now to the n minus 1. So 1 power less than the one that was in front. And then another number in front of x to the n take away 2. And I keep doing this until I get to the very end where I just have some number by itself. All polynomials look like this. And the highest power of x that you see, the highest power, is called the degree of the polynomial. And the number in front of that is called the leading coefficient. Now, there is one thing I have to say about those powers. Those powers up there, those n powers, these have to be non-negative integers. In order to be a polynomial, the powers on the x's have to be non-negative integers. That means 0, 1, 2, 3, 4, 5, 6, 7, 8. You cannot have a fractional power. If you have a fractional power, it's just not a polynomial anymore. You can't have a negative power, or else you're not looking at a polynomial anymore. Polynomials have to be non-negative integers. So here's some examples. How about this one? F of x equals x to the third minus 4x squared minus 3x plus 12. That is a polynomial function. It actually has 4 terms. What is the degree of this polynomial? 3, right? So the degree of this would be 3. What would the leading coefficient be? I'm going to put LC for leading coefficient. Is that okay? LC?
Would it be 1? Or
Yep, 1. It's the number in front of the x cubed. That is a polynomial. All right. So right now, we just want to make sure we understand. If I write a polynomial down, you need to know what you're looking at. So that's a polynomial. The next thing, next example, how about this one? Is that a polynomial? Yeah, it's arranged different. It's looks like the highest power of x we have is 8, right? But it's at the back. That's okay. Now, what about, hold on, it has x to the 8th. It doesn't have an x to the 7th or x to the 6th or x to the 5th. It has an x to the 4th. Doesn't have an x cubed, x squared, x. Is that okay? Well, with a polynomial, you don't have to have all the little pieces in between, okay? Because you could theoretically look at this as being x negative 1 x to the 8th plus 0 x to the 7th plus 0 x to the 6th plus 0 x to the 5th. And then you have plus x to the 4th plus 0 x cubed. So do you see that you could look at that as a bunch of numbers in front of different powers of x? The only ones that really matter, though, are this one and that one, right? Those are the only two that have something other than 0 in front of them. So this is a polynomial still. The degree of a polynomial, this polynomial would be what? 8. It's the highest power of x we see. And the leading coefficient is the number in front of the highest power, which is that -1, right? -1. All right, so do you think if I give you a polynomial function, you could find the degree and leading coefficient pretty easily? And that's usually doesn't require a lot of work, just looking at it.
Yes.
I'll give you another one just to make sure we're all on the same page. What about this one? Is that a polynomial?
Yes.
How can I rewrite this? How can I rewrite 1 over x? X to the -1, right? Isn't that property of exponents? If you have a negative exponent, you can drop it down to the bottom. Or if it's down the bottom, you can push it up to the top with the negative exponent. Do you all agree that those are the same expressions? So do you see that that's a negative number? And you can't have a negative. To be a polynomial, can't be negative. So this would not be a polynomial function. That makes sense at home?
yes, sir.
Yes, sir.
Okay. Also, if I gave you something like this, x to the 4th plus the square root of x, that would not be a polynomial either, because this is the same as x to the 1/2 power. And so that would not work. Has to be non-negative integer powers. Now, we still got a little time. Our goal here is to be able to graph these, okay? We want to be able to graph them, just like we know how to graph a line, we know how to graph a quadratic function. So the question becomes, what do these look like, right? What do polynomials look like? So I'm going to tell you about their characteristics. All polynomials, when you graph them, are smooth and continuous. So what I mean by smooth is that there's no jagged edges, no corners. It's nice and smooth, okay? Think about a straight line, right? A straight line, that is a polynomial. It's a degree 1 polynomial. All lines are smooth. Parabolas are also polynomials. They're smooth. Continuous means we can draw them without picking up our pencils. So whether you draw a line or a parabola, you can draw it without picking up your pencil. The question is, what about beyond the line and the parabola? What do they look like? Well, they're smooth and continuous. I can tell you that. I can also tell you this. If n is greater than 2 or equal to 2, so n is the degree, right? If the degree is greater or equal to greater than or equal to 2, then it's curved. See, because if n is 1, you're looking at a line, right? And a line is not curved. But if n is bigger than or equal to 2, then I'm telling you it must be curvy looking. All right? So here's some examples, all right? And I think the best way to do some examples is to actually just go to some graphing software. Where's my, there we go. Let's just graph something. I'm just going to make something up. Let's do x cubed minus 2x squared minus 3x plus 12. Make it minus 12. 3, no, minus, let's go plus 6. Hold on a second. 4x. There we go. So there's a graph of a particular polynomial function. X cubed minus 2x squared minus 4x plus 8. Notice it's curved, right? It's smooth, it's continuous. And it looks like from the picture that if you were to extend this, the graph would go down forever and up forever on the right. Do y'all see that? Looks like the left side goes down, the right side goes up. Let me do another one. That was x to the 3rd power. Let me do something with an even power. X raised to the 6th minus 4x to the 4th. All right, can y'all see that one? Look at that one. Smooth and curved, right? Smooth and curved. Continuous. What does it look like happens here on the left and right hand sides? Left side, what does it look like is happening? Keeps going up and up and up, right? Goes up. Right side, up. Right. Both sides going up. What happened in the previous one? The left side was down, wasn't it? And the right side was up. Do another one. How about we've done an even odd? Let me put a negative in front. Negative 2x cubed plus 8x. There's another one. Smooth, curved, continuous, right? Looks like the left side goes up and the right side goes down here, right? So look, all of these have the same characteristics in terms of they're all smooth, right? They're all smooth, they're all continuous. All smooth, all continuous. If n is bigger than 2, they're curved. But there's something even more important that we can establish. It's called, it comes from what's called the leading coefficient test. This is a pretty important test. LCT is what I'll call it from here on out. The LCT is a test that you can run to easily determine what the function is going to look like on the left and right. So with all polynomials, your left side's either going to go up or down, and your right side's either going to go up or down. Okay, how does this test determine that? So what I do is we're going to make a table. All right, so right here on the table, I'm going to put LC positive, LC negative. Over here, I'm going to put degree even, degree odd. So think about any polynomial I give you. You should be able to look at the degree, right? And just tell me what the number is. That number is either going to be even or odd. And then the number in front of that, that leading coefficient, is either going to be positive or negative. So this table will tell you what happens in each case. So if your degree is even, okay, if your degree is even, you're going to look across this row. If your degree is odd, you're going to look across here. If your leading coefficient is positive, you look down this column. Leading coefficient is negative, you look down this column. So here's what happens. If your degree is even and your leading coefficient is positive, the left side of your polynomial will go up, and the right side of your polynomial guaranteed will go up. And in the middle, put a big question mark, because that depends on the polynomial itself. We could have all sorts of crazy stuff happening in the middle. Now, if your degree is even and your leading coefficient is negative, all it does is flips that over and makes it go down on the left and down on the right. And in the middle, again, we don't know. Now, if your degree is odd, the left side will go down and the right side will go up. And in the middle, we actually don't know. And then if it's odd degree and negative leading coefficient, it flips that over and it goes up on the left and down on the right. Those are the only four possibilities when it comes to polynomials. They're either both going to go up, both down, left down, right up, or left up, right down. That's the only things that can happen. So when we go back and look at, which one is right here? How about this one right here? This example. Degree 3, so we have an odd coefficient, right? And the leading coefficient is positive. What should happen here? What should the left side do? Left side should go down, and the right side should go up. And in the middle, I don't know. What about on this one? X to the 4th minus x to the 8th. Both down, right? Because it's even with a negative coefficient, they both go down. Question mark in the middle. So here's kind of where we are. We want to be able to graph these, okay? We want to be able to graph those. I want to be able to hand you this function right here next class. I want to be able to give you this and then ask you to go graph it. So the first thing you're going to do is you're going to say, all right, well, here's what I can tell you. The left side goes down, the right side goes up, right? And you don't know what's going on in the middle. That's the first thing you're going to do. And what we will discuss at the beginning of class next time is, well, then if we want to graph it, all we'll do is try and figure out if it has any x-intercepts. Because if I can figure out where the x-intercepts are, then I know it goes down on one side and up on the other. I can start to connect these x-intercepts together with smooth curves. Make sense? Now, it's a little more complicated than that, but that's the general idea. Okay, how do we do this? So we're going to need to find the x-intercepts. And how do we find the x-intercepts for any function? Equal it to 0. And that's going to be the hard part. Because now we're going to have to take equations like that and set them equal to 0, which generally is difficult. I mean, we have the quadratic formula, but I already told you last time, the cubic formula you don't want to use, right? 4th degree formula, is like 3 pages long. And after 4, you don't have formulas. So do we have a way of attacking polynomials that are complicated and hard to factor? And the answer is yes and no. We do have some more methods that you may not have learned yet. And if those methods fail, then we just have to give up and wait till we get calculus. Then calculus helps us do it. Calculus gives us another tool to do it, but we can't get the carriage in front of the horse. We have to just work with what we have at this point. So that's pretty much what next class is going to be about. We're gonna start trying to graph these. And so, yeah, it'll be an exciting day. Hopefully it'll be good. That's all I've got for today. So make sure you do your homework on quadratic inequalities. Do that take-home quiz problem. I'll send out an email. And for those of you who are here, if you want to upload that to the link I send, just do that. You don't have to bring it in person. Any questions?
Can we get a quick shot of the quiz problem again?
Yes. Let me zoom it out a little bit. Well, I don't know if I don't know how much that's probably too small, huh? Here's what I'll do. I'm just gonna take a quick little export of that page as a PDF and I'll send it in the chat. That work?
Yes, sir. Thank you.
Mm-hmm. That's all I've got. So if you're happy, you're free to go.
Thank you. Have a nice day.
Yep, you too.
I kind of need to stick around and talk if you have a couple minutes.
I do. Yeah, so today is 10.
Thank you.
Bye. 10-4 quiz. Okay, let me put this in the chat real quick. And maybe, oh, I think everyone's gone, so. Okay, there, it should have gone through there. Give me a minute, Amanda. All right, are we good here? We're good? Okay.